I'm not really sure what I can do to get up to speed, but yeah, I'll just get started with the content. Before we start, I want to get through some things about FiveHive. This review session was prepared by me, Ionized Alpha Particle, as a part of FiveHive. It's led by Lance. It's a volunteer organization. It has a lot of volunteers. It gives many volunteer hours, and through FiveHive you can provide resources for students taking AP classes, or you can do lectures like I'm doing that helps other AP students. If you want resources, exams, questions, check out the FiveHive website. And if you want to contribute to FiveHive, click the document that will send in the chat, I guess, for more information. And once you complete your application, they'll reach back out to you in a couple weeks, I think. To start, let's look at some position, velocity, and acceleration. Think back to Physics 1 if you've taken Physics 1, or think to calculus if you're taking calculus. Position is essentially displacement, the change in position of an object or a particle in open space. Velocity is how fast it travels. Acceleration is a rate of change of velocity. Essentially what I just said. Position is how far an object is moved. Velocity is a change in position with respect to time. And acceleration is a change in velocity with respect to time. If I direct your attention to the bottom of the screen, if we start off with x, we know that the derivative of x is velocity, which if we take the derivative of, if we take the derivative of velocity, you get acceleration, and that is also the second derivative of the position, and that will be useful where they give you the position equation and they require you to find the acceleration at a certain value of time. Are there any questions yet? No. Okay. Let's dive into an example immediately. Given the equation for a position of a particle, x of t equals 1/2 t cubed plus 4t, derive the equation for its velocity, then find its acceleration. Now, we just saw that velocity is the first derivative of position, and acceleration is the first derivative of velocity, or the second derivative of position. So let's just get started with velocity. So v of t equals x prime of t. And this is a very simple power rule application. We just bring down the 3 and subtract the exponent by 1. So we know that v of t equals 3 over 2 t squared. For a variable with the power of 1, it goes away, so it's plus 4. Now from velocity, we know that the first derivative of velocity is the acceleration. So we can just differentiate velocity to get the acceleration function. So here, a of t is simply the derivative of this function right here. You bring down the 2, subtract it by 1, you get 3t. The derivative of a constant is 0, so this brings a of t is equal to 3t. It's as simple as that. Do we have any questions about how I brought that about? Is something wrong with my mic? Okay, awesome, because you said W mic. Okay, yeah. Does acceleration have a derivative? It technically does. It's called jerk. That's the third derivative of position. But for the scope of like AP physics, both Physics 1 and Physics C, you literally do not have to worry about jerk. There's also snap, crackle, and pop. That's the 4th, 5th, and 6th derivative of position. For now, it's just a factoid to keep in mind. It's just fun to say. You don't have to worry about it at all. Oh my Oregon. The integral of position is a cursed topic. We don't talk about it. Do we have any questions about this example? If not, we can move on. I'm a junior. No, I do not live in Florida. Okay, so I'll just like move on to what's next. We can also go the other way, right? When we're given acceleration, how do we derive velocity or position? Not acceleration, I should say position. Given acceleration, how can we derive velocity or position? Or how about finding position given velocity? It's just going backwards from A, and let's think about this, right? How do we revert an integral? The opposite of a derivative is the integral. The opposite of an integral is the derivative. That's the fundamental theorem of calculus. If you have taken that part of calculus yet. So here we have A, and in order to get V, we simply integrate A of t with respect to time. In order to get the position, we integrate the velocity, and that's that. So that answers this question as well. How about finding position given velocity? Let's move on. Now let's take a look at the second example. Given the equation for velocity of a particle, v of t equals 4t squared plus 6t plus 3, derive the equation for its acceleration, then find its displacement. Okay, so, well, acceleration, that's just the integral of velocity, right? Or, sorry, the derivative of velocity, right? So we just say v prime of t is equal to a of t. And once we differentiate v of t, we get 8t plus 6. And that is the a of t function. To find the displacement, like we saw in the previous slide, we integrate v of t. So we can say that x of t equals the integral of v of t dt. And also, guys, it's very, very important, like when you're doing FRQs, that you write all this down, right? You write the definition down, because that's almost always a point. So if you, in the off chance that you have no idea how to answer this question on an FRQ, if you just write down the definition of A of t, you can genuinely farm points on FRQs. So just saying like an extra point in the position you don't know anything, or you don't know how to do any, like how to answer this question, you can just write down the definition and you'll get a point, right? That said, let's integrate v of t. Once again, this is a very simple power rule application, but for the integral definition. If we integrate 4t squared, we get 4 over 3t cubed plus the integral of 6t is going to be 3t squared, and the integral of a constant is just the multiplication by the variable of integration, and that gets 3t. There is also technically a plus c at the end, but a lot of times in physics, you'll see that things start at 0 at t equals 0, so a lot of times c is going to be 0. Let me check for questions really quickly. Am I Indian? Yeah. Also, let's stick to questions about the lecture so we don't derail. Does this lecture cover 1D kinematics? So since we're doing the entirety of Unit 1, we'll cover both 1D and 2D. Would Physics C teacher explain the calculus involved with these questions more? I mean, I would think so. If you want me to explain the calculus, I can slow down and explain it to you. I think my teacher kind of glossed over the calculus, but since I already had some calculus background, I was able to pick it up pretty quickly. Do you want me to slow down and do the calculus a little bit more granularly? I mean, what do the other people think? Y'all want me to slow down? Am I going too fast? Okay, yeah. Then I'll keep the. Oh, go faster. Okay. I'm not gonna go faster just in case it goes too fast. I'll keep the pace I'm at right now then, and just for the sake of explaining it more, the rule I used here is the power law of integration. If you have like a times t to the n, and you're trying to integrate this, the power rule says the integral of this is a times t to the power of n plus 1 over n plus 1. Right, and that's essentially what I used in this question here, right? We have 4t cubed. In this case, the 4 is it's 4t squared, and the n is 2, right? 2 plus 1 is 3, and you divide that by 3, and you get 4 over 3 t cubed. Same logic applied for the 60, and for 3, it's not the same logic because you just got to know when there's no variable, you're going to multiply by t. Yeah, it is also provided on the sheet. Okay, so do y'all have any questions about this page? If not, I'm gonna move on. Okay, I'm assuming there's no questions, so I'll move on. Now let's look at some motion graphs. This is a pretty large part of mechanics, or mechanics and kinematics in general. You're gonna have to know how to analyze these motion graphs pretty efficiently. You're gonna have to be able to make conclusions about motion graphs in a lot of FRQs and a lot of MCQs. Before we look deeply into motion graphs, I'm gonna establish some intuition, see how much we know about motion graphs. If the acceleration of an object is constant, what can we say about the velocity of the particle, and what can we say about the displacement of the particle, or the position graph of the particle? I'm just gonna wait for some of y'all to put the answer in the chat, and I'll also give my own explanation at the end. Yeah. So yeah, we know since acceleration is constant, let's just draw the acceleration graph here because it always helps to visualize. Also, now that I said that, on the AP exam, guys, this applies for both Physics 1 and Physics C, since I know both the physics guys are here. When you're taking the MCQ or the FRQ, once you read the question, it always helps to visualize what you're reading, right? Because a lot of times they're gonna try to confuse you. College Board, they will try to confuse you as much as possible with really convoluted language. So it always helps to put down what the words say in images, so you know what you're looking at. So that said, we know the acceleration of an object is constant, right? So that means it's like a horizontal line on the graph. This could be like 8 meters per second squared, or if it's in free fall, it could be negative 9.8 meters per second squared, right? And since we know that the acceleration is the derivative of velocity, we now know that the slope of the velocity graph has to be constant, right? So that means this could be like, for when acceleration is 8.8 meters per second squared, the velocity would look something like this, that just a diagonal line, right? And since we know that the velocity is the slope of position, we know that the position graph has to be a curve, because the derivative of a curve is defined by a diagonal line, so it could look something like this, a parabola, perchance. Yep, linear and quadratic. If acceleration is constant, there's no change in velocity, so that means position is changing at a constant rate. Yeah, so if there's no questions about this, I can move on to the next slide. Okay, yeah, I'm gonna take a move to the next slide. Okay, so let's look at the three main rules then. There are three graphs and there are three rules essentially. With the x graph, we know the slope is velocity and the concavity is a sign of acceleration. Now the concavity is a second derivative, right? If you've taken calculus, you will know that f double prime is going to give you the sign of concavity, and therefore, since acceleration is a second derivative of position, we know that the concavity is going to tell us if the acceleration is positive or negative, and that'll tell us if velocity is increasing or decreasing. For a v of t, the slope gives us the acceleration, the area under the curve gives us delta x, and therefore displacement. The a of t graph, the slope, I know someone asked about this earlier, right? I saw that question come in, so I put that in there. The slope of the acceleration graph is a jerk, and this is unused in the scope of AP Physics, any AP Physics class. And the area under the acceleration curve is velocity. What's the second derivative in terms of calculus since derivatives are changed? The second derivative. Yeah, exactly. Yeah. Oh dang! You self-study BC, bro. That's amazing. Jerk is just not used. It's obsolete essentially. Oh really? That's cool. Yeah. Quad mechanics. That's cool. Yeah, yeah. If you're interested, you should totally take mechanics in college. I'm gonna do that for sure. Yeah. So that said, I'll take a move to the next slide. And here are some common pitfalls on FRQs, right? When you're describing graphs, never say it curves upward. That's super vague. What college will want you to do a lot of times is say concave up, positive acceleration, increasing velocity, that kind of thing. When you're describing position graphs, and it's often also thought that the shape of the position graph shows the shape of motion. Sometimes that's true, a lot of times it's not. It just shows you the direction of motion and what the change in position is. It's not going to show you like what the shape of the motion is. Now let's look at an example. Determine the shape of the x of t, v of t, and a of t graphs of a ball being thrown up and caught with no horizontal motion. Okay, so what do we know of acceleration in this situation? Yep, it's negative 9.8. It's negative 9.8 because it's in free fall a lot of the time. It's always not in free fall. It's always gonna have the negative 9.8 vertical acceleration. That never goes away. So negative 9.8, and the acceleration is going to look like this. I'm going to change colors because I feel like it can help with differentiation here. Go blue. And now let's look at velocity. We know that the acceleration is constant, right? So we know velocity has to be a diagonal line. And we also know that the acceleration is a constant negative, therefore the slope of the velocity graph has to be a negative, right? So it can't be this. It can't be that, right? So it has to be something like this, because the slope here is negative. And I want to take a pause here and tell you why this is the line and not something like this. And this really stems from just imagining the ball being thrown and caught. When you throw the ball up, it has a positive velocity, right? Since you're throwing it up, sign convention suggests that velocity is positive, and therefore the initial velocity is also positive. Here, velocity is 0. And what does that mean? That means the ball is at its peak. It means it's not moving. There is a momentary pause in motion of the ball at the peak because that's where it changes the direction of its motion from up to down. And in order to change direction, you need to have an acceleration, and in this case, that's where velocity is completely 0. And then it falls down, and since it's falling down, the velocity is negative. Now let's take a look at the position graph, right? And I'm going to change the colors again so I can differentiate. What do we think the position is going to look like? Yep, it's a parabola. It's a parabola, yeah. In this case, it's just going to be a parabola. I told you before that the graph isn't going to describe the shape of motion, but in this case, it pretty closely resembles it. But I think this is one of those exceptions. It's not always going to show you the shape of motion. Now let's take a look at what this graph is telling us, right? It's showing that at t equals 0, the position is 0. It's at what we decide as ground level, which is the hand. At t equals t1, let's say, a lot of times College Board will say t equals t1, t equals ta, t equals t2, something like that on FRQs. At t equals t1, it's approximately at its peak, and that means it's reached its maximum height, right? And this line I just drew will be like a huge blaring light, because here it's showing you that it's a tangent line. The velocity, the slope is 0, therefore the velocity is 0 at t equals t1, and that is why here the velocity graph is 0. And then it comes back down to x equals 0, which means it's back in the hand. So these are the three graphs. Notice how I started at the acceleration graph, because in these situations we know immediately that acceleration is a constant. So from there you can reconstruct essentially the other two graphs. It starts at 0, you throw it up, reaches 10 meters away from you, and then it comes back to 0. That the times will be a shorter time. What do you mean by wouldn't the time be a shorter time? Oh yeah. Yeah, that's just my bad for a pretty bad drawing. That's why I said at t equals t1 it's at the peak, and at t equals t1 the velocity is 0, because I realized my graph was a pretty bad graph. Yeah, that's just my bad for drawing a bad graph. The time at the peak is half the time at the end. Yeah, that's true. That is true. That's a nice observation. That'll actually be used later on in the course as well. A lot of the questions they ask you will look like that. If there aren't any questions, I'm going to move on to the next. Drag is more like a forces concept, so I'm not really going to do it in kinematics. A lot of times they'll actually like give you a drag force equation, and they ask you to connect it to kinematics. But that's a forces lecture. In physics 1, you disregard air resistance. Yeah, in physics C, you sometimes regard it. Okay, at a glance, if x of t is concave up, acceleration is positive, velocity is increasing. If x of t is concave down, acceleration is negative, velocity is decreasing. If v of t is a line of constant slope, the acceleration is 0, like we saw in previous examples. Now let's dive into some of that kinematics. Here is where mechanics really becomes what mechanics is known for. There are 4 kinematics equations. Your best friend when it comes to kinematics is mostly gonna be delta x equals v naught t plus 1/2 at squared. Then there's v final equals v naught plus at. And then there is v final squared equals v naught squared plus 2a delta x. And there's also one that's not on the formula sheet, and that's delta x equals v plus v naught all over 2. Are these gonna turn calculized? Oh, yeah, you mean like, are we gonna apply calculus to it? Oh yeah, you do have to multiply that t. My bad. Yeah. Thanks for catching that. It's on me. Oh yeah, these are all constant acceleration. We'll look at what happens when acceleration is negative or not. When acceleration is not constant later on. Yeah. So actually, now we're gonna derive the main equations, right? And thank you, Nimity, for that segue. Cause yeah, acceleration has to be assumed constant. So let's say a equals a, right? A is constant, and I want to derive the main equations here, so that if you forget the equation, and it's on the formula sheet, but if you like lose your formula sheet or something and you forget the equations, you can always derive them. If you want to find velocity, we take the integral, right? And the integral of a, which is a constant number, is going to be at. And there's always an initial condition, which is v naught, right? So when we integrate, we'll get some value, right? Some value in this case is at, and then there's plus c, right? We don't know that in this case c is 0, so we're gonna add the initial velocity because that's what it is, right? Yeah, in this case we don't have bounds because there's not really, we're just deriving things here. That's one way you can derive it. And from here you can derive the position equation. So delta x is equal to the integral of v of t dt. And once you integrate that, you'll see that this becomes 1/2 at squared plus v naught t plus c, right? And here we don't know that position, the initial position 0, right? So c, what we can do here is just 1/2 at squared plus v naught t plus x naught. So that's the initial position. A lot of times you'll see position as x naught. I think that's how it is on the formula sheet as well, if I'm not mistaken. So you can just derive all of this. It's helpful sometimes. It can give you a deeper understanding of what's happening. Yeah, this is all on the formula sheet, so I guess you don't really have to derive it, but it's just, I think it's cool to see it being derived and understanding where it comes from. But I just want to iterate again, this all hinges on the fact that acceleration is constant. Moving on, let's look at an example. A particle moves along the x-axis with the velocity given by the equation v of t equals 3t squared minus 2t. If the particle is at x equals 0 at t equals 0, so that's our initial condition, where is it at t equals 2? How are we going to get to position given velocity, guys? Yes, integrate. Yeah, we are going to integrate v of t to get the position. Let me just write it out real quick. From 0 to 2. In this case, we do have bounds, and that is because we're trying to see what the change in position is in the 2-second interval, and that is exactly what an integral gives you, right? And once you integrate, we see that this is equal to t cubed minus t squared. Apply the bounds. It's going to give you 8 minus 4 minus 0, and that's going to give 4. So this is delta x, right? In this case, that is the answer. This is the answer. But a lot of times, to make it harder, College Board might give you the initial x is maybe 3, right? So instead of just saying delta x is 4 and leaving that as the answer, we're going to have to say x naught plus delta x equals xf. And this is what we're trying to find out, right? We know delta x, that's 4. We now know, or we know what x naught is. We've known it for a long time. Now we know it's x equals 0. So 0 plus 4 equals 0. Or 0 plus 4 equals 4. If in case that we're told x is equal to 3 at t equals 0, we can just say x naught is 3 and we add 4 to it and that becomes 7. But in this case, the answer is just 4. Alright, I'm assuming there are no questions, so I'll move on. Now also we got 2D kinematics and projectile motion. When there are two dimensions of motion, x and y, that's when we diverge from 1D motion and into 2D kinematics. The strategy for whenever you look at or come across a 2D kinematics question or problem, the initial instinct is to split up the motion into x and y axis equations and then move on from there. And it's also important to realize that x and y are completely independent in this situation, except for the dependence on time. There is one tiny connection there with time, and it's that the time for the x-axis is 2 times the time for the y-axis. And it's also important to note that for the x-axis, acceleration is always equal to 0, okay? And that's because there isn't any air resistance or drag that we have to take into account for 2D kinematics at this point. And we'll have to do component decomposition. And for the y-axis, the acceleration is obviously 9.8. If we're on Earth, that's the gravitational acceleration. Let's just look at some component decomposition for the x-axis. Let's say that we're being launched at a theta equals 25 degrees, right? And to split up the motion into x and y, all we really have to do is take one of the equations, right? So let's say we have v equals v naught plus at. We can really just say, okay, v cosine theta equals v naught cosine theta plus at, but here acceleration is 0, and this isn't supposed to be v cosine theta, it's just vx. That's one way we can decompose it. For the y-axis, it's sine theta, so we can say vy equals v sine theta plus at. Yeah, it's the angle from the horizontal. Yeah, so if you're looking at the x-axis, you decompose it into cosine theta. If you're doing y-axis, you decompose it into sine theta. That's just the general rule here. There are also times you have to really look at the diagram for it, and then you have to decide if you want to use cosine or sine. And there are times where you use sine for x and cosine for y, but that's very limited, and for those questions, you'll have to draw it out to understand. Alright, moving on. Projectile motion. This is one of the most common applications of 2D kinematics. We'll see. A ball is launched at 30 degrees above the horizontal at a v equals 20 meters per second from ground level. Find the time of flight, the range, and the max height. Amazing. This is a very, very common projectile motion 2D kinematics question. This is also seen in AP Physics 1. A lot of this is Physics 1, but just a bit of calculus. The initial thing, the first thing you should do when you see a 2D kinematics question is draw out what's known as a VTAX VF chart. It's a trick that it's a method that my teacher used when she taught it. I think it's very, very, it makes it very easy to see what you're working with. You get the x and the y, and you draw down what you have for VTA, x, and V final. For this situation, the horizontal velocity is v cosine theta, right? So we can just write that down there. So it's just v cosine theta. And for y, it's v sine theta. We don't know t. We're trying to find t. We know that for horizontal motion, acceleration is 0. We know that for y, it's negative 9.8. The delta x for the x-axis, that's what we're trying to find. We're also trying to find that for y. And for VF, since there's no acceleration, it just becomes cosine theta. For y, we can say for 1/2 of the motion, so from ground level to the peak, the VF is going to become 0. Now, what do y'all think we solve for first? Max x? Okay, yeah. Y'all mean like the range? Where y equals 0. That is the range, yeah. Okay, I mean we could do that. So delta x equals v naught t plus 1/2 at squared, right? Here's the thing. So what I was hoping y'all would say is, solve for max height or solve for t. And that's apparent because when acceleration is 0 in the horizontal direction, you're given that delta x equals v naught t, right? And we don't know the range, so we can't really find the t just yet. So I think the first, how do I have to erase all of it? The first thing is to solve for t. And that is done. Are there any questions? All right, I'm assuming there aren't any questions. All right. So first, let's just list out the kinematics equations we know, right? So v naught equals, VF equals v naught plus at. VF squared equals v naught squared plus 2a delta x. So here we know that for the y-axis, VF is going to be 0 and v naught is v sine theta, right? So if VF is 0, we can say that v sine theta minus gt is equal to 0. Then we can say gt is equal to v sine theta and if we divide g or divide both sides by g, this g goes away and you get t equals v sine theta over g. Once we punch that into a calculator, let me just do that real quick, we should get the t it takes for the ball to go from ground level to max height. Also, it's important to make sure that y'all's calculators are in degree mode when you do this, because the only time you do radians in physics is in oscillations. So we know that v is 20 sine theta, so sine 30 degrees, over g, which is 9.8. So t is equal to 1.02. Let's leave it at that, seconds. So we can say 1.02 seconds. And since we know for x it's just 2 times the y, we can just multiply 1.02 by 2, and that should give 2.04 for the x direction, right? So that gives you the time of flight. The range then you could do from this equation right here, delta x equals v naught t. We know that for the x direction, v naught is v cosine theta. Multiply that by the time, 2.04, and that should give you 20 times cosine theta, 35.3 meters. So the last thing we have to solve for is the peak height in the y direction, and we can do that by applying the same equation here, delta y equals, oh my god, it's getting crammed. Do y'all mind if I erase all of this, or do y'all want some of this to stay here, or stay here? Can I erase what's on the board so I can get some more space, or do y'all want it there? Oh. Well, I'll just erase it because it gets easier for me. We know that delta y equals v naught t plus 1/2 gt squared, right? So we know that v is 20 sine theta, so 20 sine theta times the time, 1.02, plus 1/2 negative 9.8 times 1.02 squared. That's delta y. Once you plug that into the calculator, you get 20 sine theta. You get that delta y is 5.1. So that's the max height. I hope that made sense. Do y'all have any questions? No? Okay, is it possible to learn AP Physics 2? I'm not the right person to ask. That is definitely another way you could do it. I just use the first method that people often think of, so they know what to do, but that is definitely a way you can do that. Moving on, there is some important insight that we should see about projectile motion at when the object is at its peak. The vertical velocity is 0, but the acceleration is still 9.8 meters per second squared. I've seen many of my friends get tripped up about when velocity is 0, when acceleration is not 0. A lot of times they would say here both the Vy and Ay are 0, and that's just not true. The vertical acceleration is always 9.8 meters per second squared. That never changes unless you're on a different planet. In that case, it's the gravitational acceleration for that planet. It never becomes 0 for the vertical axis. For the horizontal axis, velocity is never 0 because there is no acceleration in the horizontal direction, and it's always equal to the initial acceleration or initial velocity since there is no horizontal acceleration. So when do these kinematic equations break? When can we not use this? Acceleration is never 0. Exactly, yeah. We can never use kinematic equations when acceleration is not constant, right? So we have a of t equals 3t. It varies with time. A of t equals 3 sine t. That also varies with time. So we can't use kinematics when we're given essentially an equation for acceleration. We could find out what the acceleration at a given time is and use kinematics to say, actually you can't use kinematics there because the acceleration always changes. So there's varying acceleration, and it always requires integration to figure out velocity and position. You can use kinematics when acceleration is constant, such as when a is equal to g, a is -3 when you're braking a car, a is 6 when you're speeding up, or any constant value for that matter. Here you can use kinematics. Now let's take a look at an example. Considering that acceleration of an object is given by the equation a of t equals 6t minus 2, determine its velocity and displacement at t equals 5, given that v equals 3 and x equals 0 at t equals 0. If you notice, this is very similar to what we did in the beginning of the lecture, but I think it's still important to address it in this manner, so we have some practice on the ways that College Board can spring this up on you. To find the velocity is integrate. So the rule is v of t equals the integral of a of t dt, and the bounds are 0 to 5, since we're trying to find out the velocity and displacement at t equals 5. And once we integrate, we know that it's going to be 6t squared over 2 minus 2t, and that gives you 3t squared minus 2t from 0 to 5. Oh. Wait, apologies. You don't do the, you can find the change in velocity like this, but to find the equation, you don't apply bounds to it. To find the change in velocity, 25 times 3, that's 75 minus 10, and that's equal to 65. So we know that delta v equals 65, and since we know that at t equals 0, v is 3, vf is going to equal 65 plus 3, and that's equal to 68. So we know what the velocity is at t equals 5. Now, in order to find position, you have to realize that the velocity equation is 3t squared minus 2t plus 3, right? Because when we integrate without any bounds, you'll get a plus c, but we know the initial condition is 3. So we integrate again to find delta x, and that should give t cubed minus 2 over 2t squared plus 3t from 0 to 5. And that's 5 cubed minus 25 minus or plus 15, and that is equal to 115. So we know that the delta x is 115, but since the initial position was 0, the final position is going to be 115 plus 0, which gives 115. Now we're going to look at some relative motion. This is a pretty large part of mechanics. There aren't too many questions about relative motion on the exam, but it's still pretty good to know. So yeah, let's just dive into it. The general formula for velocity or relative velocity, which comes under relative motion, is the velocity of A as observed from B is equal to the velocity of A minus the velocity of B. Let's dive into an example. Car A moves east at 25 meters per second. Car B also moves east at 15 meters per second. What is car A's velocity as seen from car B? How about the other way around? What do we think, guys? What do you think? Yeah, I mean, the transitive property is something that's not really tested, so I kind of omitted it. I talked to my physics teacher about it. She said that oftentimes you don't have to really worry about transitive property too much, so I didn't go too much in depth about it. Yeah, so it is 10 and negative 10. So do we need an explanation for this or nah? Because I mean, it really is just 25 minus 15 and 15 minus 25. So it's 10 and negative 10. Yeah. Okay, so let's just keep moving on. If a man is walking at 2 meters per second towards the west end of a train that is moving at 10 meters per second to the east, what is the speed of the man relative to the ground? So this is somewhat of a different type of question of relative velocity, but I think it's still pretty important to know. Since we're on the ground, we're not moving, but the train and the man are moving. And the way I like to think about this kind of equation or this kind of question is like something called net velocity. It's not an official term from what I know. It's not taught, but I just think of it as net velocity. We know that in a train that's moving to the right at 10 meters per second, if we assign the right as east and the left as west, there is a man within the train that's moving to the west at 2 meters per second, and we're watching this unfold from the ground here. Since he's essentially counteracting the motion to the right by 2 meters, we can just say that our perspective is that this man is still moving to the right at 10 minus 2 meters per second, which is 8 meters per second. And that is the speed of the man relative to the ground. Yeah, this is transitive. I just didn't give the general equation for it. Sorry to disappoint you, Infinity. But yeah, this is 8 meters per second. And that's really all there is to relative motion for now. There is also 2D relative motion, but that's not in the CED. So yeah, we're not going to go too much in depth to that. And I mean, if you really want to know, it's just splitting velocity into X and Y components and then looking at the same thing as we did here. So let's just move on to the next part, which is exam strategy, and I think this is a pretty important part of it. Apart from the actual content, since exam strategy is how we're going to pace yourself, what to expect, things like that. Top things to watch out for: using kinematics equations when acceleration is varying. You can't do that. You simply just can't. If you do that, it's going to be wrong. In this case, you have to integrate the acceleration to get velocity in position like we saw earlier in the lecture. Splitting the equation into components. When it comes to 2D kinematics, when there are two directions, splitting the components is a must. And splitting the equation into components, oh my god, did I? Alright, yeah, that's it. The key takeaways: if you forget a kinematics equations, derive it. Like we saw earlier in the lecture, you can derive it by just setting acceleration to a constant. The slope and area in the graphs give you velocity, acceleration, or displacement. Especially in FRQs, if you do the experimental design graphs, you have to decide what the slope is going to be and how are you going to use that slope, right? For example, in Physics C, E&M, there was an FRQ where they asked you to find the slope and they asked you to decide what the slope is going to be for resistivity, to find out what the resistivity is of a material. And sometimes the slope isn't going to be very straightforward. If the slope is just the constant you're looking for, you can just find the slope of the graph. But a lot of times it'll be something like the constant you're trying to find divided by something. So you're going to have to multiply by the denominator to find what the slope is and what the constant you're looking for is. And once again, integrate when a is not constant. Not doing this is a grave mistake. Don't do this. Integrate. And like I said, relative motion is a lot like net force. it can help to think about what net velocity is for a lot of the scenarios you'll see. Are there any questions at this time? Because now we're going to go into Q&A. Unit vectors are a part of Unit 2, I'm pretty sure, because that's when my teacher taught it. What do you recommend? If it is Unit 1. Well, I mean, if they're Unit 1, I can probably go over them pretty simply. Before that, yeah, okay, I mean, yeah, just do practice, progress checks, watch some videos. Yeah, expand for cues, things like that. If unit vectors are not, or vectors are not Unit 2, let me just go over them really quickly. So a lot of times in equations, you'll see something like r hat in some formula sheets, and what that is, it's a lot of times just going to be equal to 1, right? And for adding vectors, if we're given a vector that looks like this and a vector that looks like this, we want to add them together. What we have to do is do something called tail to edge addition of vectors. So you can't add them together like this, but you have to add them together like this. And you can also do this by splitting it up into x and y. If you're given the angle from the horizontal, say if this is theta and this is v and this is v and this is theta, you can split both of these up into their x and y components, and that can be done with, let's say this is 1, this is 2. The x is just going to be v1 cosine theta and v2 cosine theta. Y is going to be v1 sine theta, v2 sine theta. And to find the magnitude of the two components, you have to do x squared plus y squared, and that's going to give you the final vector. Yeah, the I hat, j hat, and k hat stuff. Yeah. Are there any more questions? Yeah, that's it. This is it for the content part of it. So if there, I'm just like asking if there are any questions so I can clear any confusion that may exist. Yeah, I'll post them on this channel after I'm done with the lecture. After like everyone leaves, I'll put in the slides here. Yeah.